My name is Jessica Kosie, and I'm currently a postdoctoral research fellow in the Princeton Baby Lab. Today I'm going to tell you about using pupillometry to investigate how infants process dynamically unfolding stimuli. You may not realize it, but it's not easy being a baby. In their everyday lives, infants are almost continuously immersed in dynamic input that both unfolds rapidly and is fleeting. So often, just as soon as it appears, it's gone. Despite this, infants learn quickly. For example, in their first year of life, they begin to understand and produce many different activity sequences. And they go from not being able to talk at all to combining a few words to speaking in full sentences over just the first couple of years. But how features of infants' rich dynamic input influences their processing and learning is a central question in infancy research. Despite this, much of the existing work on infants' development has focused on infants' overall attention to their input, and to whether or not infants have learned later at test. We know much less about how features of infants' everyday input influences processing online, as it's happening in real time. This is likely in large part due to the fact that there are very few methods to measure infants' online processing, especially measures that are infant-friendly. However, pupillometry is one way to do this. I'm sure most of you are familiar, but briefly, in addition to reacting to light, pupil diameter involuntarily changes in response to cognitive stimuli. Specifically, pupils tend to become larger with increases in cognitive engagement, and is an indirect measure of an underlying neural response. Recently, there's been a surge in interest in using pupillometry to measure infants' online processing. Several researchers have led the way in this area, measuring infants' pupil response to violations of expectation, possible versus impossible sequences, infant-directed speech, and language switching in speech to bilingual infants. Like most tools for investigating human behavior, there's a diverse landscape of possible ways to implement pupillometry techniques. Exactly which of these techniques one uses depends on a variety of things, including, importantly, the research question they wish to answer. So my goal for today is to showcase the benefits and complexities of using pupillometry with a developmental population. I'll do this by discussing the considerations and the principal decisions that I made for navigating this landscape in my own work, with the caveat that there are many ways to navigate these complexities, and exactly how you do it might differ depending on your research question. As I implemented these decisions in my own work, I relied heavily on this paper by Habetch and Listerman. I highly recommend it as an incredibly useful resource if you're thinking about using pupillometry with infants. And while my own work focuses on action processing, the general principles I'll discuss today apply much more broadly. To help orient you to my research area, I'm going to start by giving you just a little bit of background about action processing. Action processing is something we do all the time, but you're probably not even consciously aware that you're doing it. As adults, we've become so good at quickly making sense of action that it seems effortless, and it's easy to underestimate the knowledge and expertise that goes into processing unfolding activity. As a consequence, we don't fully appreciate the learning challenge that infants face when they encounter novel action for the first time. Let's watch this slightly sped up sequence of unfolding action that I imagine most of you are familiar with. You probably quickly recognize that she's making a pot of coffee. One of the skills that we've acquired as adults that's made us so good at processing action like this is the ability to quickly find structure in action as it unfolds. In particular, we quickly and readily identify individual action units that comprise this complex, continuous action stream. So without thinking much about it, you probably all generally agree on the fact that she added water to the pot, she put in a filter, she added coffee grounds, and she turned on the coffee maker. And you probably also generally agree on the approximate juncture at which each of these segments of actions started and ended. This was first demonstrated in the early 60s by Darren Knudsen and colleagues. And they found that when they explicitly asked participants to find the beginning and ending of action segments, there was remarkable consistency across adults in the junctures that they nominated as boundaries. Event boundaries demarcate action units, and they also contain important information about goal completion, as well as transitions into what's going to happen next. And finding these boundaries between units is important, as the skill is predictive of understanding, remembering, and generating action oneself. However, this method that Knudsen and colleagues used of asking participants to explicitly identify event units isn't very informative. Its overall goal is to understand how people process events as they unfold in real time. That is, it's less important to know whether observers can identify event boundaries when explicitly asked to do so. And it's more important to know whether observers implicitly attend to boundaries or preferentially sample at boundaries as they naturally view unfolding activity. And this has been the focus of recent research with adults. Using a variety of methods, including the Dalton paradigm and fMRI, researchers have demonstrated that even without instructions to find event boundaries, adults do preferentially target them in their processing. And recently, my colleagues and I have also demonstrated that adults' pupils dilate at junctures corresponding to event boundaries. So if we return to this action sequence I showed you earlier, here I'm kind of zooming in to the frames that represent the part of the action stream during which the actor is placing a filter into the coffee pot. The center slide represents the boundary. So this is the moment at which she's completed the action of inserting the filter. And if I were to draw for you a line that represented pupil dilation to the sequence, it would look something like this. What we find is that boundaries garner extra attention. Pupil dilation tends to ramp up in advance of boundaries, and it slowly returns to baseline afterward. But if it's so important to attend to event boundaries, and adults are so good at it, a primary question I've been interested in is how the skill develops over time. In particular, how do infants start to find boundaries in action as it unfolds? There is considerable evidence, stemming back to a seminal study by Baldwin and colleagues in 2001, that infants are sensitive to boundaries that demarcate units with an unfolding activity. And recent research has confirmed and extended these findings. So for example, Sohn and colleagues demonstrated that infants were more likely to remember objects when they appeared at action boundaries. And in another piece of work, Sohn and colleagues showed that infants' memory for action is impaired if it's shown with occlusions at boundaries. So altogether, it seems that like adults, infants do target and preferentially attend to boundary to information occurring at action boundaries, and at least some kinds of activity sequences. But less is known about how they acquire this skill. So how do they figure out where these important boundaries are occurring? And how might features of infants' naturalistic, everyday experience help them find help them find structure in the input that they perceive? Specifically, it may be the case that the caregiver's infant-directed behaviors during their interactions with infants provide at least one cue to structure as activity unfolds. In the domain of language, for example, you might be familiar with motherese or infant-directed speech. Caregiver speech to infants often features characteristics like exaggerated pitch contours, overall higher pitch, their speech is more repetitive, and their utterances are shorter. And these modifications appear to engage infants' attention. Additionally, there's increasing evidence that motherese facilitates infants' ability to find structure, like words, in language. In the early 2000s, an action analog of motherese was discovered. It turns out that caregivers similarly modify action in interactions with infants. So motionese, as it's called, or infant-directed action, tends to have exaggerated range of motion, increased enthusiasm and repetition. It tends to be more interactive, simpler, and motionese tends to be performed more in the infant space. And we believe that motionese and motherese co-occur throughout infancy and early childhood. Like motherese, there is evidence that infants prefer to view motionese over adult-directed demonstrations, but the extent to which motionese helps infants find structure in action hasn't yet been explored. We know that the ability to target boundaries is important for understanding, remembering, and generating action oneself. Perhaps what motionese does is it helps infants target these informative regions of unfolding events. But to truly understand the extent to which motionese influences infants' processing of action as it unfolds over time, we need a way to index processing to unfolding activity, which led me to using pupillometry. The overarching question guiding this work concerned the extent to which motionese influences infants' detection of structure or boundaries within unfolding action. Our pre-registered prediction was that infants' pupil dilation would be larger to boundaries in motionese or infant-directed over adult-directed demonstrations. And this would suggest that motionese helps infants find and increase engagement with these highly informative boundary regions. But to answer this question and examine infants' response to motionese and adult-directed action, we did a set of stimuli for infants to view. So we invited infants and their caregivers to the lab, and we had caregivers demonstrate a set of objects, first to their own infant and then to another adult. From the resulting corpus of videos, we selected a subset to present to a new group of infants who we measured pupil dilation with. Some of the videos depicted a caregiver demonstrating an action to her own infant, and others depicted the same caregiver demonstrating the same action to an adult. So I'll show you an example of one set of demonstration pairs look like. This is the mom demonstrating an object to her own infant. And this is the same mom, but here she's demonstrating the same action on the same object to an adult. And so what you might have noticed is that in the infant-directed videos, she's smiling more, she's leaning forward, she's engaged with her interaction partner, and she emphasizes the moment at which the ball sticks to the table. And that's the event boundary. But in any experiment, there are methodological considerations to be made at multiple levels. For example, there are considerations related to the specific research question you're asking. For example, we had a number of criteria for choosing the action demonstrations we ended up using, and we engaged in a number of validation efforts. But there are also considerations with respect to the method you're using to ask that research question. And these question-related versus method-related issues often overlap and can sometimes be at odds with each other. For the purposes of this talk, I'm going to focus on the second type of issues, those related to using pupillometry. Many of the things I'm about to discuss are common knowledge for people who use pupillometry regularly. There's not really a new concern with infants, but these common considerations may be exacerbated when you're trying to work with an infant population. So first, probably the most well-known cause of pupil dilation is a response to luminance. Pupils dilate when it gets dark and constrict in the light. Thus, luminance issues are a primary concern in pupillometry research. And this is one place where there are many different options and many different opinions. One option is to make stimuli isoluminant, meaning that luminance is equated across the images and videos. So here's an example still image from one of my videos. And this is the same image after being passed through a Matlab program that makes the image isoluminant. Now recall that we were interested in infants' response to naturalistic stimuli. And unfortunately, this isoluminant version looks far from natural. I will note that this is just a quick pass of the image through a Matlab program, and there are likely ways we could have optimized the stimuli to make the isoluminant version look less weird. Nonetheless, the isoluminant version would never look like the naturalistic stimuli. So we opted not to make our stimuli isoluminant. But I will point out that isoluminant stimuli may be less problematic for other types of studies. For example, these are the original and isoluminant images from a study by Mira Nencheva and colleagues. They were interested in infants' response to auditory stimuli, and the goal of this visual was to help hold infants' attention. And you can see here that the isoluminant version looks much less weird and worked just fine for their purposes. So isoluminance expects different stimuli differently, and may be more problematic if you want to keep stimuli naturalistic. However, while we opted not to use isoluminant stimuli, of course the luminance issues didn't just go away. And there are a variety of ways to ameliorate or account for possible luminance-related effects. We found it useful to take a multi-pronged approach to addressing luminance concerns. So first, when creating stimuli, one can try to balance luminance across conditions as much as possible. For example, we had all caregivers demonstrating objects in front of the same background at the same table, wearing the same t-shirt, so we made the videos look as similar as possible. You can also measure luminance across your videos, for example, to each frame, and test whether luminance values are equated across dimensions of interest. In our case, we wanted to make sure that videos depicting motionese were not systematically higher or lower in luminance than adult-directed versions. Finally, once you've measured luminance, it can be included as a predictor in analyses to help demonstrate that the predicted effects, in my case pupil dilation at boundaries, hold up even when taking luminance into account. Another consideration in conducting pupillometry research with infants concerns holding infants' attention. Of course, this is a general issue in any research with young participants. However, it can be even more important when you're doing pupillometry research. Some reasons to think carefully about how to keep infants engaged are more obvious. For example, to even acquire information about infants' pupil dilation, they have to be looking at the stimuli. And it's helpful to keep them looking as much as possible. One reason for this is that there might be luminance changes related to looking away from the screen and then back. Also, getting as many trials as possible helps when you're trying to average out random fluctuations in pupil dilation that may be unrelated to processing of the stimulus. Infancy researchers have a lot of experience thinking about how to hold infants' attention. One way to do this is simply to keep the stimuli engaging. For example, I used video clips of caregivers and toys. Infants like people and faces. They're interested in novel toys. We also kept each video clip short, ranging from 6 to 12 seconds. So these stimuli seemed likely to keep infants interested. Another way to hold infants' attention is to regularly add what are called attention getter trials. And this helps keep infants engaged, or to re-engage infants when they're starting to get fussy or uninterested. And it turns out that this is the very best way to get infants' attention. I borrowed this laughing baby clip from the Many Babies study of infants' preference for infant over adult directed speech, and it's a really good way to get infants oriented back to the screen. Finally, it's important to take into account the timeline of pupil dilation. How long after a stimulus onset might you expect to see a pupil dilation occur? The time course of infants' pupil dilation likely depends on a number of factors, including age and task. For example, it's likely that the time course of infants' pupil dilation response becomes more adult-like over time. But this may vary depending on features such as task difficulty. To our knowledge, there hasn't been a systematic investigation into how pupil dilation might differ across infants and adults, which makes it questionable to take the timing of pupil responses from previous adult-related research and use the same timing to inform research with infants. However, there is some research suggesting that across a few different tasks, infants' pupil dilation response may be slower than adults. A slightly different, but nonetheless very important issue involves the refractory period of the pupil dilation response. If you're trying to examine pupil dilation in response to a series of events, it's important to provide opportunities for the pupil to return to baseline before presenting the next event of interest. For example, I mentioned those attention getter trials earlier. As you can probably imagine, infants' pupils are likely to dilate in response to a laughing baby. So you'd want to give adequate time after the laughing baby for their pupils to return to baseline. In my own work, I attempted to create a task structure that dealt with the issues I've been discussing. And so this is the structure of my experiment. At the start of each block, infants viewed that laughing baby attention getter for 8 seconds. I also had an attention getter at the start of each trial. This was a set of looming circles with a chime playing in the background. A gray screen indicated the start of each trial. And then we showed the first still frame of the video. And this was both to get infants used to the visual scene and to control for changes in luminance that might occur in response to this first frame. To give infants' pupils the opportunity to dilate and return to baseline in response to each of these events, we opted to play the trial attention getter, the gray screen, and the first still frame for 3 seconds each. The video then plays silently. After infants viewed the video, the next trial starts with the chimes, the gray screen, the still frame, and the video sequence. After a block of 6 trials, 3 motionees and 3 adult-directed videos, the laughing baby plays again, and the next block starts. Infants viewed up to 6 blocks, or 36 trials. Altogether, this took about 11 minutes. But of course, not all infants got through all 6 blocks, and there was considerable variability in the number of blocks and trials that infants got through. But despite this, we were pleasantly surprised with how many trials infants completed. All of the infants in our study got through at least 1 block. And in total, we were able to include 897 usable trials across 34 infants. So the median number of trials per infant was 29.5. While infants viewed these trials, we recorded their pupil size using a system that was recently developed by a group of researchers in the biology department at the University of Oregon. Their company is called Perceptivo, and the system is called the SIPR system, or the Stimulus-Induced Pupil Response System. They currently have a patent pending. The SIPR system is a little different from traditional systems like Toby and iLink, and the specifics of the system you're using matter. For example, how does the system find pupils, and how does it measure pupil size? How does it deal with head movements? And the beauty of the SIPR system is that this is transparent at all levels of analysis. The system was originally created for use with barn owls, so I spent some time during my PhD assisting in further development of the system for infant research. Infants sit in a car seat facing a computer monitor on which the stimulus plays. You'll notice that the infant is strapped securely into the car seat to minimize leaning forward as much as possible, and we have head supports so that their head doesn't move very much. We also work to be able to sit the infant down quickly and begin the study as soon as possible. And this is especially important with infants, otherwise they can quickly get restless and fussy and start to move a lot. It's also helpful to have the caregiver nearby. So we had the caregiver seated next to the infant, but facing the back of the room. And we asked the caregiver not to interact with their infant. With the SIPR system, we record video of infants' eyes from a Raspberry Pi infrared camera with a high-quality lens. It's connected to a Raspberry Pi computer. As you can see, the lens is flanked by infrared lights, and these help illuminate the pupil. So what we get is a close-up video of the participant's eyes, and we run these videos through a script that calculates pupil size for each frame in the video. Here's an example frame from a video taken with this system. We have a Matlab script that goes through each frame in the video. The Matlab script first pushes the image to threshold. The threshold is set based on how dark the pupil is. So anything that's as dark as the pupil is black, and the rest becomes white. You will notice that some things that aren't pupils are still black, such as eyelashes and nostrils. However, the script then finds circles, and so it'll find the pupils this way. And we can adjust the settings so that it finds circles with more or less error. So these are the circles it might find here. The script then calculates the longest diameter of the circle and uses that as the pupil size. And the reason it calculates the longest diameter is because in cases where the head turns to the right or left, for example, the horizontal diameter of the pupil decreases, but the vertical diameter of the pupil accurately reflects pupil size. So once we've run this Matlab script, we have an estimate of infant's pupil size for each frame in the video, and we're able to synchronize these estimates with the time at which stimuli were presented. Most pupillometry systems generate raw data that needs to be preprocessed. And as you'll see over the course of this workshop, researchers take very different approaches to preprocessing and analysis. Following researchers like Nash, Unsworth, and colleagues, we opted for a minimal preprocessing pathway. So to give you a sense of what this might look like, we first z-scored within each infant to correct for possible physical differences in pupil size across participants. And this was especially important for our system, given that it measures pupil diameter based on pixels in the video. So the size of the infant or distance from the camera might influence their overall pupil size. It's also good to filter pupil size values to smooth out random fluctuations within the data. And again, there are many options for filtering, but we opted to use the Hanning filter with code from Jason Geller's Gazer package. We inspected the data before and after filtering, and the Hanning filter appeared to successfully eliminate random fluctuations while preserving the general shape of the data. We next calculated our baseline pupil size as the average pupil diameter in the 1 second region before the onset of the video. And we calculated baseline separately for each trial. And this is following a number of previous infant and adult pupillometry studies. All of our models are mixed effects models with demonstration type, so motionese versus adult directed, and video region or boundary versus non-boundary as fixed effects. We included random effects of subjects and videos to account for the fact that observations within subjects and observations within videos are not independent. And this helped us increase confidence in our ability to generalize our findings. To account for differences in baseline pupil size, we opted to control for baseline in our analyses. However, a more traditional way would be to subtract the baseline from each pupil size value and to use these baseline corrected values in analyses. We had pre-registered our decision to control for baseline. However, we've also run the models with baseline corrected pupil diameter values, and the findings are the same either way. To remind you of our research question, we asked, to what extent does motionese influence infant detection of structure or boundaries within unfolding activity? We predicted that pupil dilation would be larger in response to boundaries for motionese over adult-directed action. And I'll show you our results. On this figure, I have frame number on the x-axis, and I have z-scored and filtered pupil size on the y-axis. We intentionally varied the location of the boundaries in our videos, so sometimes it occurred earlier in the video, sometimes it occurred later. And this was so that timing alone couldn't account for any pupil dilation effects that we found at boundaries. So here, we're considering the boundary frame 0, as indicated by this dashed green line. The pre-boundary region is in purple, so that's the 1 second or 30 frames before the boundary occurs. The boundary region is in green. It starts at the boundary and extends for 1 second or 30 frames. And the post-boundary region is yellow. This extends for 1 second after the boundary region. And when action is adult-directed, indicated by this black dashed line, we found no significant boundary-related effects. However, for motionese demonstrations, infants appeared to be responding to boundaries, with the largest pupil diameter here in the boundary region. And this is a statistically significant effect. Also, these effects held when we measured and controlled for frame-to-frame luminance of the videos. These findings tell us that motionese seems to facilitate infants' detection of boundaries in unfolding action. It seems that something about these motionese demonstrations highlighted the location of action boundaries, or otherwise drew infants' attention to the structure of unfolding activity. Previous research has provided evidence that motionese globally enhances infants' attention. But these results fill in important gaps and provide a totally new insight into how motionese might influence infants' attention to action as it unfolds over time, and in this way potentially have downstream influences on cognitive and linguistic development. To summarize, the research I presented provides novel insight into how caregivers' use of motionese might scaffold infants' detection of structure and action. It also validates a new method, the zipper system, for examining infants' pupil dilation to streaming visual stimuli. Of course, with all pupillometry research, there are interpretive concerns that we need to grapple with. First, are there alternative factors that might have elicited the observed pupil dilation pattern? Are your assumptions about the time course of pupil dilation accurate for your age group and your experimental task? And how robust are the results to different preprocessing strategies? These are all issues we've been grappling with in our own research, and we have a variety of ideas and strategies for pursuing them in follow-up studies. So to wrap up, my goal for this talk was to outline method-related concerns for using pupillometry to measure infants' response to streaming stimuli. To this end, I walked you through these considerations in relation to a study my colleagues and I have recently conducted. In sum, I hope this talk showcased both the benefits and complexities of using pupillometry to measure infants' attention to stimuli as it unfolds over time. So I'd like to thank you for listening, and thanks to all the people who have contributed to this work in various ways. In particular, I'd like to thank my PhD advisor, Dare Baldwin, who is my primary collaborator on all phases of this project, and Avinash Bala, one of the original developers of the SIPR system, who shared his time and knowledge with me to make this work possible. And of course, I couldn't have done any of this work without all the caregivers and infants who participated in the study. Thank you.